going to talk about artificial intelligence and what's next. Okay, so for today's talk, there are 3 parts. So for the first part of the talk, I want to give you a gentle introduction to AI. What AI is about, what is AI's history, what is the current progress on AI, and how do we go from here, okay? And the second part of the talk, I will talk about some of the exciting breakthrough that we have here at UC Santa Barbara, where we build empathetic machines that can understand human emotion and also generate emotional sentences by machines from scratch. Okay, and finally, the third part, I would like to discuss with you what will be the future of AI. What are the things we need to care about? What are the challenges ahead of us? And how can we move from here to the future? Okay, so this is the agenda. But if you look at artificial intelligence, this is a picture from 60 years ago when the AI pioneers, Marvin Minsky, John McCarthy, they were thinking about, how can we develop artificial intelligence programs that can play checkers with you? How do we actually teach machines to be able to prove mathematical theorems? Okay. At that time, this all seems very difficult, and also, at that time, Marvin Minsky actually asked one of his students, just take computer vision as a side project, as a summer course, and how can we actually solve computer vision? Turned out that AI actually has huge development in the past 60 years, and AI has going so big, and even some of the sub areas can become its own area. For example, natural language processing is a specific area that I'm super excited about. In natural language processing, we teach machines to understand human language, specifically teach machines to read and write. So what will be some applications? That will be the system that you've been using, for example, Siri or Amazon Alexa, these dialogue systems, the question answering systems, the semantic search that you use with Google that tell you directly the answer, and also systems like machine translation, speech recognition. And if we make analogy that NLP is teach machines to read and write, computer vision is about teaching machines to see and understand the environment around us. So computer vision application would be things like object recognition. So given an image, can you recognize the specific animal in that image? So given a big image with many of you sitting here, can we recognize your face? Okay, so this would be another big area. The third thing I want to briefly mention is the area of robotics, where we can be able to combine computer vision, NLP, control, and all these dynamics into designing robots that can help us in certain scenarios. For example, in the nuclear leak events, how do we actually teach machines to go into the danger and be able to switch off the danger? Okay, another big area is called multi-agent system. So imagine right now what's happening with the World Cup, but what if you teach machines to be able to play soccer? So this would be RoboCop. You have multiple machines, multiple robots, and you want them to coordinate and be able to accomplish some of the complex tasks. Another area that you might not be super familiar with, this is called knowledge representation reasoning. So for human, it's very easy to understand what are the different things, but for machine, how do you represent different concepts, different objects, different locations, organizations, and people, and what are the relations among this, right? How could you automatically develop a program that allows you to do inference and be able to come up with a solution? So this is knowledge representation and reasoning. Another big area would be data mining. So data mining would be, let's say we're given the entire social network from Twitter. Can we understand from the graph with machine learning, we want to understand what are the sub-graphs, what are the sub-interest groups that can actually occur in Twitter. I have to mention that right now, one of the biggest area in AI is called machine learning. Okay, you may have heard machine learning so many times. Machine learning is all about teaching machines to learn from past experiences and be able to make predictions in the future. For example, if you look at all the tweets that happened this year, people talk about, they're getting the flu. Can you use this information to predict the flu outbreak for next year? Okay, and specifically, some of you may have heard of deep learning. Deep learning is about using deep neural networks to learn a very complex function to map the input to the output space. Specifically, deep learning is about neural network that has multiple layers and allows us to learn very complex functions to go from the input to the output space. If you look at the progress of AI these days, I have to say it is really stunning. I remember that 20, 30 years ago, when we first designed these speech recognizers, the word error rate could be about 30 or 40%. So what that means is that if you say 10 words, right, 4 or 5 of them, machines can get them wrong. But if you look at the performance on speech recognition on standard data set, we can see the performance getting extremely good. So in this case, we can actually see 95% word accuracy, right? What that means is that if you speak to your Siri, you can probably get, at most 1 word wrong out of 10 words that you say. Okay, so that performance can even be as good as some of the untrained transcribers that are actually human. Okay, another big progress is in the area of object recognition. So the picture you're seeing here is from ImageNet, which is a gigantic image database created by Stanford researchers. So they spent a lot of time and a lot of resources and created this data set that has more than 1 million images. Okay, and for 1 million images, they asked crowd workers to annotate each particular object in this image, and this has to be very fine-grained categories. For example, not just specific, just your generic house cat, but actually has to be a Madagascar cat, right? So for this particular task, if you look at the performance from about 5 to 6 years ago, the performance wasn't very good. The performance was only 70% accuracy. But if you look at the huge improvement that happened about 5 or 6 years ago, they can actually get better performance comparing to the human untrained workers. So they can get to about 95% accuracy of predicting the specific category, one of the 1,000 categories from this particular image. With all that, I would like to move on to the second part of the talk, which is about, we talk about recognition, right? Speech recognition, object recognition, but did we solve AI? Well, the answer is obviously no. So for a human, there's something that are very natural to us, for example, emotion. But can machine perceive human emotion and be able to generate sentences that have human emotions? Okay, so this is extremely difficult. But the first question you may ask me is like, why do we care, right? So why do we need to design machines that understand human emotion? I imagine that some of you might have the experiences of calling to the call centers with issues about utility, about the bills, about credit card, about your cell phone. Let's hear about what some of the callers may say.
Yes. No, I am departing from Jacksonville.
There is no Manila in Montana. Anytime.
So you can see that definitely these call centers, they got a lot of annoyed customers, right? The question is, these big companies, they're not gonna hire 10,000 people just sitting there and answer your calls. They need to cut down the costs. So we have to design automated agents to be able to deal with your requests. But because some of the requests are very difficult, they have to be able to hand it over to the human agent. So can you design systems that recognize humans' emotion when a customer gets really annoyed? Can we then switch over to the human agent? So this is very practical, and it happens a lot, and we have to find solutions to deal with this kind of issues. There are also another situations where sentiment analysis and emotion analysis is very important. For example, when you're writing your email. Right, so this little clip created by New York Times shows you how important this task is. And the challenge, like I showed you earlier, is not like we have to recognize one person. We have to actually recognize all these different kind of noise customer, right? So they speak very differently. How do we design algorithm to recognize all these different cases, and how will you be able to design systems to understand all these different type of emotions and sentiments in very different writing styles? Okay, I have to say that more or less this is relatively older problem. So sentiment analysis has been a field for about more than 10 years, and we got very good performance. So for many cases, we can get 80% accuracy when predicting the sentiment of the user. One difficult case would be, looking to the language and really trying to dig into the language and understand what's going on. For example, my colleague Dan Jurafsky, they've been looking at analyzing these restaurant reviews from Yelp. So the team went ahead and collected more than 900,000 Yelp reviews, right? They were trying to understand what's going there. And the interesting thing they found is that, by looking at this large numbers of Yelp reviews, well, they can really identify the ones that are really bad, right? For example, you look at this particular very bad one-star Yelp review, it essentially says, the bartender absolutely horrible. Waited for 10 minutes before we even got her attention. Then we had to wait 45 minutes for our entry. Stalk the waitress to get a check. She didn't make eye contact or break her stride to wait for a response. So for human, we have no problems understand this text, right? But for machine, they're not designed to understand human language. They are designed with bits. They are designed to be able to communicate with different machines, to communicate with program, okay? So how do we teach machines to understand this? Well, we have to first do a very good analysis on what is going on in these bad reviews, okay? So one common thing Dan Jurafsky and his team found is that there are a lot of negative sentiment language. For example, you will see this, words like horrible, awful, terrible, bad, disgusting. You also see words like, for example, past narratives about people that talk about, waited, didn't, was, and he or she, his or her. A lot of mention about different people in the restaurant, managers, customer, waiter, waitress, and so on and so forth. There's also a lot of mentions about we and us, right? So we can think about why there's a lot of mentions of we and us, and they tend to talk about the experience as customers. We were ignored, and then we have to wait it for a long time. The interesting thing they found with this review data is that, there are also other reviews about the same kind of language. And the interesting thing they found is that when you're looking at a genre specifically about past tense, about we and us, negative language, and people mentions, well, this is actually very similar to language of people who are suffering trauma. And when people suffer from these tragedies, they tend to use a lot of these cases to distance from the past and trying to create such distance. And also they use we to seek the solidarity in the community. And we can say that one-star reviews, they are very related to trauma narratives. And performance, like I said, to recognize 1-star versus 5-star, we can get about 80% accuracy for this task. Now, the problem hasn't solved yet, so I just talk about recognizing human emotion, right? There's another part, which is natural language generation. So how do we teach machines to generate human language? This is another thing that I'll briefly talk about. But interesting thing with this kind of corpus style study is that you can look at specifically of the language and see how that is related to drugs, dessert, and related to language about sex. So turned out that Dan Jurafsky and his team actually were able to see a lot of mentions of this sex language in food, where people talk about food porn, they talk about sexy food, seductively steered foie gras. So this is from the real data. Interesting observation is they were able to find that for the restaurants with $4 stars, you're more likely to use the language about sex to describe your food. Okay. Another interesting observation is that they also see a lot of mention about language in terms of drugs in this Yelp reviews. For example, they see things like, garlic noodle, my drug of choice. Okay, and there are things like, the fries are like crack. Interesting observation about this drug language is that it does have a very strong correlation with the cheap restaurant. And now you think, this actually makes a lot of sense, right? So you would not think, you want to say your garlic noodle is sexy, or your caviar is like crack. So this would be not happening. But this would be interesting discovery from the data set that allows us to get some, understanding about data and intuition that help us to develop machine learning algorithms to be able to recognize the sentiment of these reviews. Okay. After recognition, let's go to the very important topic, which is how do we teach machines to generate emotional language, right? So recognizing emotions from text, like I said, got 80% accuracy, but how about generate new sentences that nobody haven't seen, no one has seen it before, and be able to have that emotion? This is particularly challenging. And I have to say that deep learning works very well when there are a lot of data, and it has to be deal with the tasks that are more like a low-level recognition task. For example, object recognition and speech recognition. You have a lot of transcriptions, you have a lot of annotation, whereas in our case, if you want to generate new sentences that have specific emotion, you gotta have a corpus, which is a collection of sentences that people actually talk about specific things, and you have labels to tell machine, well, this one is negative, this one is positive, right? So first thing we ask is, how do we collect a large-scale corpus like this? Well, the reality is that we don't really have a large corpus that are annotated by human for us to develop such system. So this is a big challenge when we first started the research. Later on, we are able to came up with a solution that is to leverage the Twitter data. So my student, Shenda, went ahead and collected 500,000 of these Twitter conversations, and they essentially look at the conversation pairs where you have a specific emoji entered in the response. So for this case, when someone says something, well, a person replied and then shows some love, you see this love emoji. Now we can actually use this human annotated, naturally labeled data as the feedback allows us to train machines, okay? So in this case, we're able to get 500,000 of them, and you can see that this emojis conveys a lot about emotion, and you won't be surprised. The first one is you laugh so hard and you laugh in tears, right? So that's pretty much what you've been using very often. And there's also sad emojis, there are happy emojis. You can see obviously there are very strong correlation between emotion and emoji on this data. So we got the free data, they're all annotated, so what can we do next? Then we designed a relatively complicated machine learning system called MojiTalk. And MojiTalk is variational autoencoder system that is conditioned on some specific label. So what that means is that we can first use an encoder to encode the original message into k-dimensional vector, and then condition on the specific emoji that you want to generate to convey that emotion in the response. Now we can teach machines to decode from this latent space and be able to generate new sentences that corresponds to that original message, but also be able to convey that emotion. Now the question is, how well does it work? Well, it works relatively well, I have to say. The performance has been, really beyond our expectation. So we can look at this specific example where someone said, gee, I needed that laugh. This is the original sentence by human. Now, there are two things we want to do. We want to condition on different emojis. This essentially are the different emotions that we want to generate. So we want to generate a happy emotion on this happy face, and also want to generate the sad sentences. Let's see what's happened. So these are the designated emoji. And if you look at the new sentences generated by machine, it's pretty stunning in the sense that the happy face, it generated a sentence, good, have a good time, whereas the sad face, it generated a new sentence, no one has seen it before, says, me too, but it's a lot of me. Okay, so if you look at the result, it is somehow could be difficult for you to tell whether these are from human or is it really from machine. Okay. Another thing you may ask is how does it compare to the existing systems? Well, the existing systems actually can also get a relatively okay result. So for this case, someone streaming and this person says, "Sorry guys, was gonna stream tonight, but I, still feeling sick." So this is original message, and we want to generate two type of response by machine. So one specific response is kissing face that generate this kind of encouraging emotion, and the other one is sort of like a closing hand emoji. And let's see what happens with the generated response. So we have a baseline system based on a technique called sequence-to-sequence learning, and the result is also okay. It says, "I'm sorry, you are going to be missed it," so which is not very good. The second one is kind of weird, right? So it said, "I'm sorry for your loss." So this happens. That's the reality, right? And for Mojitalk, it generated a very interesting result. The first one Mojitalk generated is, "Hope you're okay, hon," which does seems to be very realistic. And the second one is, "Hi, Jason, I'll be praying for you." So I don't know why the machine figured out the person is Jason. It could be wrong, but you do see the praying sign, praying word, right? That corresponds to the closing hand emoji. So this is all very interesting result. Another thing we've been looking at is, how do you quantitatively evaluate the system, right? So we have some examples, but can we find a way to objectively learn the intensity of the generated sentences? Well, like I said before, if you can train a machine learning system, a classifier that can recognize human emotions, right? So you'll be able to predict the emotion. So what if we train the emotional classifier on the side, on external data, and be able to run this classifier on the generated sentences from different systems, including Mojitalk. So in this way, we can have a relatively objective way to be able to measure the quality and intensity of the emotions generated by different systems. Okay, so in this case, we're actually able to find that Mojitalk got best performance, so that is the reinforced CVAE model, to get close to 80% accuracy in terms of getting the top 5 accuracy in predicting the emoji. Okay, there are a couple of lessons that we learned from the design of Mojitalk. One thing is that we found it's definitely possible to be able to teach machines to learn human emotion and be able to generate new sentences about emotional sentences. But you have to find a good way to generate the data. And second thing I want to mention, as you can see, some of the examples are not great, right? So there's still a lot of challenges ahead of us. How can we design systems that can generate indistinguishable responses that really look like a human-generated sentences. Finally, I also want to give a shout out to my intern. Shenda was actually an undergrad student who worked with me last summer only for 2 months, and he published this paper at the top venue in computational linguistics this year, which will be presented next month in Melbourne, Australia. With all that, I would like to move on to the last part of my talk, which is really about the future of AI, right? If you look at the future of AI, I have to say this is really exciting. If you compare the number of papers in all fields that was published in 1996 to 2016, you see about 2 times increase, right? If you look at computer science, in general, the increase is about 6 times. And if you look at at AI in computer science in terms of number of publications, number of research papers in this area, you get close to 10 times, right? So you can see that the trend is definitely very positive, and AI has a lot of future. On the other hand, I also want to mention that AI is hard. There are a lot of challenges ahead of us. For example, can you tell the difference between a bagel and a dog, right? So this is a funny example, but there are this kind of corner cases, right? There are harder cases that we still need to work on. For example, can you tell which one is a chihuahua, which one is a muffin? You know, sometimes even for human, you need to have a second look to make sure that we do really get to the correct answer. And how about this one? The fried chicken versus labradoodle. Right, and you know, you can always find all these different cases, right? There's, you know, dog and sheepdog and mob. How do we get from here 80%, 90% accuracy to 100% accuracy? So there are still a lot of work we need to do. So there are a lot of challenges ahead of us. We didn't solve any problem. I think right now we only have some little achievements at this stage. The road is still very long ahead of us. I also want to show you some of the amazing research developed by IBM researchers that only got released this year, where they built a debater.
A lot of times they don't have a clear bottom line win. Otherwise, we wouldn't debate things.
According to rules set by the candidates themselves.
What we are trying to accomplish here is really to demonstrate that we can have a meaningful and valuable discussion between man and machine.
We are actually trying to show that a computer system can add, if you want, conversation or decision making by bringing facts and doing a different kind of argumentation.
Hello, Dan. Thank you for the opportunity to be here today.
The debater system tries to understand the concept over which we are debating.
Having analyzed the data, I will argue that we should subsidize music education.
When it gets the topic, until you hear the first speech, it's collecting all the possible arguments, trying to remove redundancy.
It is about recognizing important issues for society.
The system is evolving.
The IBM Debater can have all the opinions in the world, but IBM Debater does not pay taxes, and we do.
You are speaking at the extremely fast rate of 218 words per minute. There is no need to hurry.
The value of the technology is really to allow decision makers to take more informed decisions. There is a territory which is uncharted to some extent, and this is where we are now.
Yes, so I think the message is here. AI has to be for everyone, right? So not just for computer scientists, not just for programmers, but it has to be able to serve everyone. Everyone needs data analytic tools. How many documents can you read a day? Can you read 1 million documents? You can't, but AI can do that, okay? So we really need the capability to help us to be able to analyze data better. Second thing I want to mention is that AI definitely can serve us better, right? Can get us to have a higher life quality. For example, for the disabled people, they couldn't drive, but if you have driverless cars technology, well, they can get to anywhere they want. And another message I want to get is that we have to be aware of the social issues when we're designing these AI systems. What are the biases from the system? How do we mitigate the biases, right? How do we understand accountability and interpretability from the system? And how can we teach AI systems to benefit the human society?